For the 2026 Promoting Electric Propulsion competition, the William and Mary Boat Racing Team set out to push beyond our limits and redefine the performance of our electric race boat. With a focus on speed, efficiency, and control, we're engineered critical systems across the entire platform. From propulsion and structural improvements to electrical reliability and advanced control systems, every design decision was driven by performance on the water. Join us as we walk you through the work behind our 2026 PEP competition entry.
Hi, I'm unmanned. I'm a senior here at William and Mary, and today I'll be walking you through the electronics of our boat. So we start off here first with our 48 volt battery that has a 60 amp hour capacity. It then leads us to our 400 amp fuse here, and then our main switch. Our main switch then connects us to our 48 volts here, which power our ESCs, which then power our motors, which are underneath our electronics board. We are then taken to our 12 volt converter, and this converter then powers our rudder configuration and our pumps, as well as our telemetry tower back here. We are then taken to our 7.5 bus, which powers our servo motors, which then will power our active air components. Okay, so additionally we have our new and improved electronics board. It is secured by 2 bolts, and then also geometrically secured by 3D parts we designed and printed here in-house. So like I was saying, this is our new electronics board. Our old electronics board used to be placed right here, and then the wires were nowhere near as organized as this. Our new vision, we have the organization was a priority, and because the old wires were bent all over the place, and this caused EMF interference, as well as the wires could then fall into places that we did not want them, like the drivetrain or other areas where there just could be a catastrophe. I'd also like to note that that our new wires are also EMF shielding to prevent further EMF interference. Along with strapping down all of the wires on the board, we also have wire mounts on the side of the boat to constrain the wires further, along with connectorizing all of the wires. Now moving on to the drivetrain, we are running 15 kilowatt motors, and the rods that we chose for the internal portion of the drivetrain, we chose aluminum rods to save weight. Now, aluminum is a softer metal, and because of this, we ran into some issues. The main issue was we were hearing a resonant frequency, and this was causing the shaft to then whip and warp at around 4,000 RPMs, and this was very bad. Okay, this is the FEA analysis from the video in Fusion 360. And as you can see, the FEA analysis agrees with the video that you just saw. So to prevent this issue from happening and continuing to damage our drivetrain, we then created a drive shaft carrier for our rods. And as you can see here, we 3D printed it. We designed and 3D printed it. This is PLA and carbon fiber with the carbon fiber shaft in between. And then we have a mount right here to the boat using a high strength epoxy with then nylon 6 and carbon fiber and our radial ball bearings. This has successfully neutralized the issue of the whipping and the warping.
Hello, my name is Ben Montforth. I'm a senior at William Mary, also on the boat team. I'll be talking about our rudder configuration today. So as you can see, if we go over here, our rudder is controlled by a 150 kilogram servo. That serves as our main component in the actual rudder steering. We then have tied onto our servo wheel, this modular component, 2 ropes with 2 turnbuckles to increase the tension as necessary for the rudder steering, connected to the actual rudder component that turns as necessary. As you can see, controlled by our RC controller. Now the rudder can turn 90 degrees across, as restricted by these two bolts. You can go all the way here and all the way here, and this can be adjusted as we need, shorter or larger turning radius. Now the reason we needed this updated steering configuration is because our previous configuration that involved differential steering and skegs weren't as efficient. With the differential steering, we had one prop turn slower than another prop that was turning faster. And while this was an effective way of turning right and left, it was not the most efficient. Number one, it just increased hydrodynamic drag in the water, as this one prop would be turning slower and dragging through the water. But number two, it also reduced thrust and acceleration overall, especially around turns, which this track requires on competition day. We would need to slow down one of the props and increase our turning radius at a slower speed, which is just not efficient in a competitive race environment. Additionally, with the skegs, yes, again, an effective way to increase alignment of the boat, but very draggy as well. So when you can combine the skegs, drag, and differential steering, hydrodynamic drag, and reduced thrust, we just weren't reaching the goals we set for ourselves and what our motors are capable of. Now, entering the rudder, this not only allows for the propellers to spin at the same speed and turning as well. We can spin it at as high as the RPM allows us in our motor, but our turning radius decreases really significantly. We have about 3 inches across and 6 inches down, 18 inches of squared cross-sectional area in the water that allows us for increased straight line tracking, increased maneuverability around turns, and just increased safety for both of those reasons as well. If we need to avoid another boat, if we need to avoid an obstacle, or anything like that. Another problem that we faced previously was the speed of deployment and just overall efficiency in deploying the boat. This is because our old hatch had about 20 holes that needed to be screwed in with M3 screws to seal the boat and also to take things off. Now, obviously this is slow when trying to put the boat in the water and getting all the screws in, but it also poses a significant safety risk. If there was a loose wire or a misconnected ground in our electrical system, it would take way more time to unscrew all those 20 bolts and figure out the problem before a fire started. So to combat this issue, we created a cam clamp system where we have 4 main bolts here attached to the underside of the hull that allow us to just slide in our hatch and press it down to already have somewhat of a tight seal, but then we just take 4 cam clamps and screw them on very efficiently here and then tighten them down, which then lead us to cutting our deployment time and also safety risk by factors of 2 to 3. So as you know, one of the requirements of the tournament is to carry a 30-pound payload. And at the beginning of this semester, we were concerned of where to place the payload, how to distribute it, because our configuration was very different inside the electronics. We didn't have space really for a 30-pound payload. Additionally, we were facing significant issues trying to plane the boat. We would always kind of get up on about a 10 to 20 degree pitch, which was really dangerous for flipping over, and it would never really plane. We needed something that would create a little bit more downforce in the front to get the boat on the plane. Our solution after we reconfigured our electrical system and moved it more central was this weighted payload blanket that sits on the inside of the boat, right on where the previous electrical system was, and increases the downforce on the front of the boat and moves up the center of mass significantly. So we can get on planes easier and still hit the requirement of the 30-pound payload.
Hey, my name is Michael Kelly Galdames, and I'm the team captain of the William and Mary racing boat team. One of the things that we have struggled over the past is that transition between displacement and plating. Although we experimented with a lot of things, one of the things that really focused on was on some of the issues that we were having on the stern. While doing some testing, we actually noticed that there was a lot of sucking air in this area, which led us to actually do a lot of CFD analysis, which we actually found out that there was indeed a low pressure area in this portion of the boat. So we started like creating different models of the boat, and as you can see here with these 3D printed models, we came out with different ideas, trying to create tunnels, trying to create changing that height of the top of the stern. And to do that, to test that in real life, we actually implemented temporary foam platforms where, as you can see, we still have some residuals from the glue that we use in order to like implement that foam. We ended up covering all this area with foam, which actually resulted in an improvement, and we actually were able to achieve planing. However, in the same testing of that, we were actually doing a lot of prop testing, which has been the main issues that we have so far. And as you can see, we in our propeller graveyard, we have tested with different materials, additive materials, as well as creating our own combinations of materials. Like, for example, this one is an ASA with metal meshing in order to like try to increase the strength of them. We have created different shapes, different sizes, trying to do different blades. However, none of this was actually a solution until we landed on a really good design, which is a lot more hydrodynamic. Not only it's a lot more hydrodynamic, but it also actually have this cup right here, which has allowed us to stop losing a lot of thrust to the sides, which we actually notice in this, guys. So this one actually creates a lot more vector in the direction that we want of the thrust. And although we have experimented with different materials, so far we have found that the material that we never really thought about, which is PETG, has resulted to be the best material so far. So after taking these props back and putting them on the boat, even though initially the foam actually resulted in an improvement and helped us achieve planing, we started realizing that even though we were routing the water and guiding the water onto the propellers, one of the main issues that we were having those low pressure problems was actually the propeller design. So what we did next is that using these same propellers, we actually started changing the shape of the foam, reducing the foam until we went back to the original settings. And we found that actually we were just able to get on a plane even more efficiently, because now, we didn't have the drag created by the foam. So one of the really cool things that we're testing this year is an active aerodynamic system. One of the things that we first struggled was we just struggled so much with getting on a plane that we started studying a lot of different solutions. One of the solutions that we landed on was, what if we had this active aerodynamic system that is able to produce downforce when you most need it? So one of the things that we noticed with our boat is that the nose of the boat was coming too high right at the point where it was about to get on the plane, and it was becoming too dangerous. It was becoming like maybe 15 to 20 degrees. So the idea is that at some point your boat is going to start rising, and by changing the angles of your canards, you can actually bring this down and produce a lot of downforce when you need it at the nose. And dynamically, this will force the nose of the boat to actually come down. And that's solution number one. The other solution that is also obtained by having this system is that at high speeds, we're familiar with the typical boat that will be going super fast and then just flies off and flips away. So this, one of the ideas that we have is that now that we experience at higher and higher speeds with this boat, is that we also want to bring safety into the system. So these systems right now are not fully integrated yet. Right now we are controlling with a remote control, but the idea is that we're going to be running a script inside of our Orange Cube, which is the microcontroller, which actually integrates all the data that it receives from. We have multiple GPS and magnetometers, but this guy also has a magnetometer and accelerometer inside of it, which will actually allow us to read data as the pitch of the boat as well as the speed of the boat. Together with this system, as we explained before, is that we had to upgrade our electrical system. One of the big upgrades that we have to do now that we have the canards integrated to it is that we actually needed to increase the power on our 12 volts voltage divider. So we are actually about to install this guy, which will allow us to safely run all the new systems. So going back to the orange view, one of the things that this guy will actually allow us to do as well is to control the boat autonomously. So not only is going to be controlling the canards in real time, but actually we're going to be able to map the course that we want to do for the race. And the idea is that the boat will just go from point A to point B and then do that turning radius and come back home safely.
Hi, I'm Megan. I'm a sophomore and I joined the boat team last semester.
Hi, I'm Kira. I'm also a sophomore and I also joined the boat team last semester. So we were in charge of making the battery cage because originally we had 4 of these batteries, which totaled to like 100 amp hours and 125 pounds in just battery alone. But since the race went from 5 miles to 2 miles, we were able to consolidate into one battery that was 60 amp hours and cut the weight down to 80 pounds.
For our battery cage, we used fusion. So originally we had a bunch of foam sandwiching our battery, which it wasn't the best solution. So we decided to make a battery cage using fusion. We had a few iterations just from dimensions. So when we originally created it, we made the walls of the battery too thick, and so they would run into the drive shafts. So when we redid it, we made sure to do it right, and we did a bunch of new dimensions for printing.
We also ran it through FEA simulation. I think we did 100 pounds on 100 pounds of force on each side, and we got like a safety factor of 2, like about 2, which means it could like withstand like 200 pounds of force on that one side. And I think after that, we thought it was good, and we confirmed that it was gonna fit in the boat, and so we sent it to printing, and I think it printed in ABS plastic.
Even though not all of the team members can make it today for the video, the boat team at William & Mary continues to grow. We get new people every day pretty much, and we're really excited because we keep providing hands-on skills to everyone, and I'm personally really excited to see where this team goes, and I know the team is as well.